Hello, everybody. So now we have finished 2 weeks in this course on algorithms for big data, and it's now time for us to take stock a little bit. We've learned a little bit about probability theory. We've looked at things like Chernoff bounds and things like. But why exactly are we learning these notions? And the key to this lies in our understanding of what we mean by algorithms for big data. When is an algorithm a big data algorithm? And just to understand this, let's contrast this with what we know to be traditional algorithms. Okay, what is a traditional algorithm? Well, we typically think of a CPU that's executing an algorithm, and that CPU has access to some data that's usually stored in the main memory. So the main memory can be accessed at random locations, and the main memory includes the program that's executing on the CPU, the input data, the scratch information that gets generated as the algorithm is executed, and the output data. Everything is included in the main memory. And moreover, typically when you run a traditional algorithm, you expect the answer to be correct. So let's look at example. For example, if you want to compute the minimum spanning tree of a graph, then you expect the algorithm to actually generate a minimum spanning tree. And the same can be said of various other algorithms. And over the last 50 years, we have a very nice, rich set of algorithms that have been developed. Uh, and over the course of time, some of the requirements have changed, and there is still a lot of need for traditional algorithms. It's not like the traditional algorithms are no longer useful, but as computer science and the applications and the world around us changes, there are new and interesting algorithmic questions that are being asked, and this is inspired by various applications that we broadly call big data applications. So, what are these big data applications, and what are these algorithms that are used to solve these big data applications? Well, and what are the characteristics that we encounter? Well, the input data is typically too large to fit into the main memory. So the traditional view that the data fits into the main memory is no longer necessarily true. And it's not just one computer that handles the data. Typically, it's a large data center that processes data. And because it's a large data center, there are multiple servers, and the data is actually broken into subparts and stored in multiple servers, and they have to interact with each other to solve problems. And finally, the data is often not allowed. You cannot access the data in traditional random access type of fashion. You have some rules by which you can access the data. So, as I mentioned, the data could be stored in a distributed setting. It could be stored in a cloud, and the only access you have is through some queries. Or, as an example here, maybe the data is stored in such a manner that you can only access the data as a single pass through the data. So maybe you get an access to the graph, a large graph, as in some arbitrary fashion where you get one edge at a time, and you have to see these edges one edge at a time, and you have to answer something about the graph. So that's one more example of way in which you can access the data. All of this implies that the traditional model of algorithm design is no longer the only model that matters. There could be a variety of ways in which we can define models of computing based on the specific architecture of the system, specific application at hand, and so on and so forth. And of course, we recall that in traditional algorithms, we require the answer to be always correct. At least typically that's our expectation. But let's think of canonical modern applications, searching in Google. Of course, we're all familiar with this I feel lucky button that Google has. So if you type something very prominent, so for example, if you type in Narendra Modi, clearly the first link that you will get will be typically what you expect because it's a very prominent search term. But if you're searching for something less prominent, then it's okay to be a little unlucky. You may, perhaps you don't require it to be the first outcome of your search. But let's say if it's within the first page, you're usually happy. Uh, so in other words, your expectation is no longer as strict as before in traditional algorithms. And it's a simple way to capture this is the phrase, it's sufficient if most of the time the output is good enough. So most of the time kind of refers to a sort of a probability theory type of thing where you want it to be correct with some good probability most of the time, and you don't necessarily need the output to be correct in the absolute sense, but you just want it to be good enough, a good approximation. So in the search engine context, you want the outcome to be good enough in the sense that the actual website that you're after, it's good enough if that appears within the top, say, 5 hits. And moreover, it's not like every time you search for something, it's always within the top 5. Let's say 99% of the time you search for something and what you're looking for is within the top 5 or within the first page. That's great. And Google it typically follows that sort of a paradigm where most of the time, 99% of the time, the website that you're looking for is within in the first page. Of course, there's times when it's not in the first page and it's but that's something you're willing to live with, and that's the essence of big data algorithms. There's a lot of therefore probability theory and approximation ideas that need to be incorporated into the algorithms. But it's not like, therefore, just because the user expectation is a little bit less, it doesn't mean that you can start to, completely lose control over the quality of the output. You still need to be careful to prove that with very good probability you get a very good answer. And this is where the theory that we are studying, the probability theory and the various algorithmic models will be helpful in designing the right type of algorithm. So without further ado, let's get started on some new ideas, models, and algorithms for big data.